hyperspace and hyperdrives. Are they the solution to the problems of interstellar travel? It's as if the universe is deliberately preventing us from conquering the galaxy. It doesn't even want to let us reach the nearest stars. Whichever method of interstellar travel you consider, there are always significant problems that arise. Sometimes they're so serious that some people are convinced that our species will never make it beyond the solar system. Flying to other stars using current engines is out of the question, as it would take tens of thousands of years even to reach the nearest system to the Sun. In principle, nothing prevents us from accelerating a spacecraft to much higher speeds, including tens of % of the speed of light. There are already many quite realistic ideas on how to do this, but here there are a lot of problems as well. It's not enough to accelerate the ship to such velocities. It also needs to survive the flight, considering that at those speeds, even a single speck of dust can cause significant damage. And this is far from the only problem. But even if we manage to overcome all these challenges, build up sufficient protection, figure out fuel, deceleration and so on, even if we learn to travel at 50% or even 90% of the speed of light, we would still only be able to explore a small neighboring region of the galaxy, well, within a reasonable time frame. That's why in science fiction, if the action unfolds not within a single planetary system but on a galactic scale, authors typically use some form of faster-than-light travel. Special relativity forbids moving faster than light. Well, as well as travel at the speed of light itself for objects with mass. Therefore, authors usually have to use some kind of a trick to bypass this limitation. Often these are the same tricks, just called by different names, depending on the author. I've already made a video about one of those tricks, warp drives. Another popular option is ships equipped with hyperdrives that travel through the universe via hyperspace. And today we're going to talk specifically about them. What is hyperspace? How are hyperdrives supposed to work? Is there even any scientific basis for this concept, and is it possible to create them? We'll talk about all that and much more. I'm Andrei, and this is Cosmos Elementary. I already talked about why, when moving through space, we can't just exceed the speed of light. We can't even reach it. Whether it's mass becoming infinite and requiring infinite energy, or time coming to a standstill and all that. For the plot of many science fiction works where characters travel across the galaxy to be even possible, some way must be found to bypass this limitation. It might seem like these are just works of fiction, so why worry about realism too much? You could simply invent some kind of magical instant travel and not bother explaining it. And some authors do exactly that, but the term science fiction includes the word science for a reason. Although, of course, the level of scientific accuracy can vary a lot. There's what's known as hard science fiction, where special attention is given to technical details and scientific plausibility. And we know that quite a few concepts have already made the leap from the pages of fiction into the real world. So, who knows, maybe the same will one day happen with ways of getting around the Lightspeed barrier. Among the popular methods found in the works of various authors, we can recall warp technology, engines that warp space-time, the use of wormholes, space-time tunnels, and hyperdrives, where a ship enters hyperspace at one point and exits it at another. All these methods have one thing in common. They're not about faster-than-light speed, but about faster-than-light travel or transport. I know, it sounds like there is not much of a difference, but actually there is. All three examples are attempts to make traveling from point A to point B faster than light at least somewhat plausible. As I've said many times, we cannot travel through space faster than light. However, this limitation does not apply to space-time itself. Moreover, we know today that there are objects in the universe right now that are receding from each other faster than the speed of light, due to faster-than-light expansion. I talked in detail about how this is possible in my video about cosmic horizons. The trick with faster-than-light movement of space itself is essentially used by the warp drive concept, where space is stretched on one side and compressed on the other, creating a bubble that can move faster than light, while the ship inside the bubble does not move through space at such a speed. An analogy is often used here as well. If we imagine a two-dimensional analogy of space-time as a fabric with a spacecraft at one point and the destination at another, with a conventional form of travel, the spacecraft would simply move along the fabric towards the desired point. But in the case of a warp drive, the ship essentially stays in place while we pull the fabric itself along with the destination toward it, effectively bringing it closer. And as I have already mentioned in my video about warp drives, such technology is not even denied by science. In fact, there are quite a few scientific papers on the subject, along with some theoretical progress. For example, the initial versions of the calculations required exotic matter with negative mass. And not only it is unclear where to get it from, but it was also required in massive quantities. In more recent calculations, however, it was possible to significantly reduce the required amount of exotic matter, or even do without it entirely. Though, sometimes those result in sub-light warp drives, which does not sound quite as appealing. In any case, the fact that they are theoretically possible does not mean we will ever be able to create them. Options involving wormholes and hyperspace attempt to bypass the light barrier by using a shortcut, or a shorter path through the universe. What if the shortest path from point A to point B is not simply flying in a straight line through space-time? On the one hand, all these methods do share some similarities and they're even often confused with one another. On the other hand, there are also fundamental differences. Many people associate warp drives primarily with Star Trek, even though that's not where they first appeared. However, Star Trek definitely popularized this technology. A similar situation applies to hyperdrives. Only here, most people know them from another popular franchise with the word star in its title. Of course, I'm talking about Star Wars. But obviously, it wasn't George Lucas who came up with the concept of hyperspace and hyperdrives. The word hyperspace is generally used in various fields of physics and mathematics, and as a rule, its use is not related to interstellar flight. But in the context of space travel specifically, the term hyperspace was likely first used in 1931. In this issue of Amazing Stories magazine, where John Campbell's novel Islands of Space was published. If this cover and the title of the work seem familiar to you, it's no coincidence. I mentioned it in my video about the warp drive as likely the first mention of warp-like technology in fiction, though the name warp drive itself wasn't actually used there. And it is remarkable that in the same work, hyperspace seems to be mentioned for the first time as a way of traveling across the universe as well. Here, hyperspace is described as a special place where the laws of physics operate differently, and within which one can travel at any speed imaginable. Here, the characters would send their ship into hyperspace, travel through it, and then emerge at a different point. The description is already quite similar to what we see in Star Wars. Even the danger of objects like stars is mentioned there. Hyperspace travel is quite popular in science fiction, although it's not always called that. A similar concept is used by Isaac Asimov and in many other works, in the Halo game series, in Warhammer 40k, and in many others. But as I've said, the general public became aware of this idea mostly thanks to Star Wars. And this visual effect of acceleration and jump into hyperspace is also known to almost everyone. There are actually a couple of interesting details here. First, a very similar concept appeared even before the first released film, A New Hope, which came out in 1977. 3 years before that, the low-budget film Dark Star was released, and this is how interstellar travel was depicted there. In Star Wars, not much attention is really given to the technical details or to explaining how interstellar travel technology actually works. In fact, it's commonly said that Star Wars isn't science fiction at all, but rather space fantasy. Another funny detail is that especially in the early films like A New Hope, the characters constantly talk about things like going at light speed, accelerating to light speed, and so on. The only problem is that at the speed of light, they wouldn't be able to travel between systems so quickly, and they would still have to fly for many years from one system to another. The whole point of using hyperspace is to travel not just at light speed, but at speeds many times faster than that. So, which is it? Light speed or hyperspace? You can also nitpick the visual effects of, as they say in older films, jumping to light speed. If we were flying at a speed approaching that of light, there would be no streaks of light, of course. Several effects would come into play simultaneously here. For example, the aberration of light would focus the light from the stars into a single point directly in front of us. And due to the Doppler effect, the wavelength of radiation from objects behind us would stretch because of redshift and conversely compress in front of us due to blue shift effects. This could shift the radiation out of the visible range. Radiation that we cannot see with our own eyes now, such as the cosmic microwave background radiation, could shift from the microwave range back into the visible spectrum as we approach the speed of light. In reality, we probably wouldn't see a glow coming from all directions. Instead, due to such extreme motion, it would be concentrated in front of us. It's also possible that inside such a spacecraft we would observe a glow related to the Unruh effect. This is an effect predicted within the framework of quantum field theory, which tells us that the vacuum of the universe is not just emptiness. Even where there is nothing we would call particles, quantum fields and fluctuations still exist. The point is that as an object accelerating very rapidly, it can sort of amplify quantum fluctuations, which may cause a glow. Furthermore, this glow would only be observed by the accelerating object, while an outside observer would not see it. Some groups of scientists have even claimed possible experimental confirmation of the Unruh effect. Well, in short, we definitely wouldn't see anything like that. But if we're talking not about near light speed travel, but specifically about traveling through hyperspace, then of course it's much harder to say what that would actually look like. At the very least, because our brains adapted to living in three spatial dimensions would struggle to perceive it. And after all, what is hyperspace? Where is it? Hyperspace is often referred to as another dimension or a space with a different number of dimensions. And by potentially moving into another dimension, one could take a shortcut and reach another point in the universe faster than light. This is the fundamental difference from warp technology. After all, it involves no extra dimensions. It only manipulates our four-dimensional 3+1 spacetime. But does this kind of method of traveling through the universe have any scientific basis at all? If we go to the Astrophysical Database website and search for warp drive, we will get hundreds of results. Not all of these scientific papers are on the topic, but many are specifically about space warping and warp technology. But if we type in hyperdrive, only a few results? And even those are almost all off topic. We can try searching for hyperspace and there are more results, but again, almost all of them are off topic. There are more results because the word hyperspace is actually used in physics and mathematics, but usually in different contexts. In short, although both technologies are quite fantastical. But on the topic of warp, there are at least some theoretical studies, there have even been some experiments, albeit somewhat questionable ones, but still. When it comes to hyperdrives, however, the situation with scientific research is quite dismal. Perhaps partially for that reason, hyperspace, unlike warp drives, is popular not only among science fiction writers, but also among various mystics and New Age fans of esoteric practices. For instance, they speculated that hyperspace could be afterlife or some kind of otherworldly realm. Or they use it to explain, for example, the allegedly mysterious disappearances in the Bermuda Triangle, like the famous case of Flight 19, where planes vanished and their wreckage was never found. There is a version claiming they supposedly could have entered another dimension. But anyway. So even if there are no or virtually no scientific papers directly dedicated to travel through hyperspace, science does discuss related and connected concepts and phenomena. So we can still draw some conclusions here about the possibility of such an idea. So hyperspace may refer to a higher dimensional region. As far as we know, you and I live in a universe with 3 spatial dimensions and 1 dimension of time. However, science does not rule out the possibility that other dimensions may exist. Some time ago, I made a separate video dedicated to the 4 spatial dimensions. If we view hyperspace as a higher dimensional space, and if we want to use it somehow to travel through the universe, then we must somehow cross over from our 3-dimensional space into, say, a 4-dimensional space, travel through it, and then emerge back into our 3-dimensional space. As is usually the case with multi-dimensional things, it's hard for us to imagine what it would look like. That's why, as usual, we resort to analogies here. In the video about the 4-dimensional universe, I talked about the book and film Flatland. As a reminder, Flatland is a flat 2-dimensional world inhabited by equally flat 2-dimensional beings. The entire plot there revolves around the main character, a square, discovering the existence of a 3-dimensional universe. When a resident of the 3-dimensional universe, a sphere, enters and visits Flatland, however, since there is one less dimension there, he cannot fit entirely, and only one of his slices exists in the 2-dimensional universe at any given moment. But then the square conversely heads into the 3-dimensional universe and it fits in there quite well. There are some nuances here, of course, but that's not so important for now. It looked something like this. And what is particularly interesting for us is that when the square finds himself in the 3D universe, he sort of rises above the plane of his universe and leaves it. Then, by moving in 3 dimensions, he can return to his plane again at a completely different point. For the inhabitants of Flatland, it would look as if a square simply teleported from one point to another. Of course, it wouldn't actually be instantaneous, since it would still have to move through 3D universe as well. In fact, the path might even end up being longer this way. But one can speculate that in hyperspace the laws of physics would work differently, or that the geometry of space is different, or that time flows differently, any of which could make the journey faster than simply traveling in a straight line through the ordinary 3-dimensional space. We can imagine ourselves in the place of the square, only in our case we would cross over into the 4D space. And just as the square disappeared from Flatland, we would disappear from our 3D universe, move through hyperspace and then reappear at another point. That is, if we were even able to survive the transition into a 4-dimensional universe, which is also not guaranteed. I've already used the game 4D Toys, and here we now see a sphere, which is effectively a slice of a 4-dimensional hypersphere. Just as here, a circle is a slice of a 3-dimensional sphere. Both variants are familiar to us, so we can easily visualize them. However, showing a hypersphere that exists in 4D space in hyperspace is already problematic. In this case, only one of its slices passes through our universe, which we perceive as a sphere. Another example that helps illustrate how travel through hyperspace could shorten the journey was given by Michio Kaku, who, by the way, has an entire book titled Hyperspace. Flatland is an example of a flat 2-dimensional universe that looks like a flat sheet extending infinitely in all directions. But we know that the universe can have different geometries. For instance, it could be closed in on itself. The inhabitants of Flatland could perfectly well live on the surface of a sphere. In that case, by moving in one direction, they would eventually return to the same point from which they started their journey. In the case of a flat 2-dimensional universe, if a resident moves into the 3rd dimension and without invoking any tricks involving different laws of physics, such a path through 3D space does not necessarily become shorter than one within the 2D surface. However, if a Flatland inhabitant moves into 3D space from a closed universe, such as a sphere or another curved shape, they could effectively cut across the geometry and reach the opposite point faster than if they traveled along the surface of the sphere. It can be assumed that the geometry of space is curved and be even more bizarre than a sphere. Then the shortcut through hyperspace could turn out to be even shorter. And by the way, it might essentially be possible to move from one point to another many times faster than a beam of light traveling through ordinary space. Some assumptions have been made here, but at least conceptually it is clear how this could work. However, there are some major caveats here. First of all, we still don't know whether other spatial dimensions actually exist. Many modern theories are built around this, specifically of course various versions of string theory, and the one that unifies the main ones, M theory. We can also mention a related concept from string theory, the idea of a brain world or brain cosmology. According to this idea, our universe could exist on a brane, from the word membrane, specifically a three-dimensional brane. If, again, for the sake of convenience, we get rid of one dimension, imagine our three-dimensional brane as a sheet. Then this sheet might be located somewhere, right? And it is embedded in what is called the bulk hyperspace. In this analogy, the room would be the bulk for this sheet, and from there one might start to wonder if this two-dimensional sheet exists within something three-dimensional. Could there be other sheets in that hyperspace as well? Other universes? Again, it is difficult for us to visualize even three-dimensional analogs of these sheets inside a four-dimensional analog of the room. But that's more or less how it should work. In theory and on paper, all of this is perfectly permissible and the calculations for such universes hold up. But so far, there is exactly zero experimental evidence for it. But let's assume it turns out that these higher dimensions do exist. And let's say we learn how to penetrate them somehow. This raises another small issue, which I mentioned in my video about a four-dimensional universe. Flatland isn't exactly a documentary, it's a work of fiction that uses analogies to explain multidimensionality perfectly, but for the book's plot to be possible, certain assumptions and simplifications are naturally made there. In the film, observing Flatland from our 3D perspective, we see the internal organs of its inhabitants, because we see absolutely everything that exists in that universe. There's simply no place where one object could hide another from our view. After all, there is no thickness there. But when an inhabitant of such a universe enters 3D, there is nothing holding their organs in place anymore. And in theory, they should actually just fall out. The same might happen to us. The moment we enter the four-dimensional space, everything we have, everything we are made of would literally fall apart. In fact, it could be even worse. The fundamental interactions could behave differently, and even the particles we are made of might start acting in a completely different way. In short, it could kill us instantly. In fiction, one could come up with some kind of protective field inside which physics would continue to operate as it does in 3D, but how to do that in reality is unknown. In short, of all the faster-than-light travel methods used in fiction, hyperdrives and hyperspace remain among the most unrealistic. But there is another method that is in many ways similar and yet has at least some scientific basis. And I've already mentioned it today. I'm talking about wormholes or Einstein-Rosen bridges. I think many of you are familiar, at least in general terms, with wormholes. And when I was talking about a shortcut from one point of the universe to another, and especially while I was waving a sheet of paper, you probably got a strong association with wormholes. And indeed, the final result is very similar, although there are also differences. In simplified terms, a wormhole is a tunnel that connects two points in space. But when describing a wormhole, they don't say that there are more spatial dimensions inside it. If a traversable wormhole could be created, there shouldn't be 4D space inside the tunnel. Wormholes can come in different forms. For example, the ones connecting two regions within the same universe are being discussed. Furthermore, if other parallel universes exist, why couldn't there be tunnels connecting two different universes? And indeed, why not? Another typical distinction is made between non-traversable and traversable wormholes. The concept of wormholes has existed for over 100 years, and not in fiction but in science. Just a few months after the emergence of the modern theory of gravity, Einstein's general relativity, in 1916 Karl Schwarzschild found solutions to Einstein's equations that implied the possible existence of objects we know today as black holes. And shortly thereafter, Austrian physicist Ludwig Flamm found additional solutions for the opposite of black holes, white holes, and a mathematical description of the object that would connect them, namely wormholes. Later, this idea was examined by Einstein and Rosen, then specifically that version of wormholes is now called the Einstein-Rosen bridge. And a lot of oddities followed from all these solutions, such as the idea that black holes could be a kind of a window to other regions or even to other mirror universes. But back then, Einstein didn't worry too much about it. After all, from a practical standpoint, it didn't present any real problems yet. So yes, if a portal like that suddenly appeared next to us and then we could simply walk through it and end up in a different universe, then yes, that would definitely be worth talking about. And besides, even if we could breach a black hole and launch, say, a probe into it, it wouldn't survive anyway and would be destroyed. And those aren't even all the problems. In general, for a very long time, such bridges were considered more of a mathematical trick, and the real possibility of their existence was not seriously considered. In 1963, Roy Kerr found new solutions to Einstein's equations that described not a static black hole like Schwarzschild's, but a rotating one. And likely this version is closer to reality. The structure of such a black hole is more complex. For example, the singularity there is not a point but a ring. And another interesting consequence is that a probe launched into such a black hole along a certain trajectory could survive the experience. However, the wormholes described by Einstein and Rosen still weren't suitable for travel, as they were unstable. And wormholes could collapse quickly upon contact with ordinary matter, causing the connection between the 2 points to break. But in 1973, the first theoretical descriptions of traversable wormholes appeared. In 1985, Carl Sagan was writing his novel Contact, and for the book's plot, he needed to come up with a realistic and scientifically accurate way of faster-than-light travel. He turned to the famous physicist Kip Thorne with this request, and ultimately Thorne and his colleagues developed a theoretical description of a traversable wormhole, and even managed to publish it in the prestigious journal Physical Review Letters. In their work, 9 conditions were set to ensure that a wormhole could be used for travel across the universe. But most importantly, to stabilize such a wormhole so that it stays open the entire time our ship is passing through it, you need exotic matter, a substance with negative mass energy. We already encountered it today when we were discussing warp drives. Some solutions have already been found there where one can do without such a substance, but with wormholes, that's not the case yet. In short, wormholes remain an exclusively theoretical construct. Yet they are possible on paper within the framework of general relativity, given certain conditions. Although there are attempts to find them through astronomical observations and even to create something similar in laboratories. The possibility of time travel is also connected to them, but perhaps we'll talk about that separately sometime. Is there any connection here to other dimensions and hyperspace? If we recall the overused explanation of wormholes using a sheet of paper, it might seem that there is. This is the one where we imagine that a sheet of two-dimensional universe and shorten the path by folding the sheet. After all, the sheet itself is two-dimensional, but when we fold it, we effectively bending it in an additional third dimension for that universe. And if we transfer this analogy to our own universe, it would look like this. The folding of our three-dimensional space would have to take place in the fourth dimension. And you can come across such reasoning. However, if we look, for example, at the mathematical description of the Einstein-Rosen bridge, it is entirely formulated within the four-dimensional space-time with 3 spatial dimensions. That is, there are no additional spatial dimensions involved here. So, in the end, traveling through hyperspace and traveling through a wormhole are not the same thing. And this is why at the beginning of the video I separated them in 3 distinct methods: warp drives, hyperspace, and wormholes. Yeah, some of them seem a bit more plausible. Well, hyperspace drives are probably the most fantastical of them all. Given our current capabilities, they are all not very different from magic. And it's unlikely that anything like this will be possible in the next hundreds or even thousands of years. Thanks for watching. Links to all of the sources are as always down below in the description. By the way, I already have a video about warp drives. Check it out if you haven't seen it. Leave a like if you enjoyed the video, comment, and subscribe for more videos in future. Bye.